Artificial intelligence plays a transformative role in industrial IoT by converting massive industrial data streams into actionable intelligence. In industrial environments, data originates from heterogeneous sources. The most common type is sensor data, which includes temperature, vibration, pressure, current, voltage, humidity, and flow measurements. These are typically high frequency time series signals. Next, we have event driven data such as alarms, fault codes, machine state transitions, and PLC logs. These are discrete and triggered by operational conditions. There is also operational and transactional data, including production counts, maintenance schedules, inventory logs, and ERP records. Additionally, modern IIoT systems collect image and video data for visual inspection and audio data for acoustic fault detection. Now let us classify this data structurally. Structured data refers to highly organized data stored in relational databases. Examples include production tables, maintenance logs, time-stamped sensor readings stored in SQL databases, and KPI records. Semi-structured data includes formats such as JSON, XML, and log files generated by industrial gateways or IoT platforms. These contain tags and metadata but do not follow rigid relational schemas. Unstructured data includes images from inspection cameras, audio recordings of machinery, video feeds, PDF maintenance manuals, and operator notes. AI techniques such as computer vision, natural language processing, and deep learning are required to extract meaningful features from this data. The ability of AI to integrate structured, semi-structured, and unstructured data is what makes industrial IoT systems intelligent and context-aware. Raw industrial data cannot be directly used in AI models. It passes through a multi-layer processing pipeline. The first stage is data acquisition through sensors and industrial communication protocols such as MQTT, OPC UA, and Modbus. At the edge layer, pre-processing tasks such as noise filtering, signal conditioning, normalization, and preliminary anomaly detection are performed. Edge AI reduces latency and bandwidth usage. After edge processing, data is transmitted to centralized servers or cloud platforms. Here, it undergoes cleaning, synchronization, aggregation, and transformation. Time alignment is especially critical because sensors operate at different sampling frequencies. Instead of feeding raw signals into models, statistical features such as mean, variance, kurtosis, skewness, and RMS values are extracted. In vibration analysis, frequency domain features are extracted using fast Fourier transform. For image data, convolutional neural networks automatically learn hierarchical features. Processed features are then stored in data lakes or industrial data warehouses for training and real-time inference. Industrial AI systems depend heavily on high-quality data. Poor data quality leads to unreliable predictions and unsafe decisions. Accuracy ensures that sensor measurements correctly represent real-world conditions. Calibration errors can significantly degrade model performance. Completeness ensures minimal missing values. Missing data due to network downtime or hardware failure must be handled using interpolation or imputation techniques. Consistency ensures uniform units, timestamp formats, and data standards across systems. Timeliness ensures low latency, which is critical for real-time predictive maintenance and closed-loop control systems. Industrial data is also characterized using the 5 V's of big data. Volume refers to the massive amount of data generated daily from high-frequency sensors and video feeds. Velocity refers to the continuous generation of streaming data that often requires real-time processing. Variety represents the coexistence of structured, semi-structured, and unstructured data forms. Veracity addresses data uncertainty, noise, and reliability issues common in harsh industrial environments. Value represents the ultimate objective of extracting actionable insights that improve efficiency, reduce downtime, and optimize production. Industrial analytics can be categorized into four levels. Descriptive analytics explains what is happening through dashboards and real time monitoring systems. Diagnostic analytics explains why it happened using correlation analysis and root cause identification techniques. Predictive analytics estimates what will happen next using machine learning models such as regression, decision trees, random forests, support vector machines, and deep neural networks. A major application is predictive maintenance. Prescriptive analytics recommends what action should be taken. Predictive models can forecast failures, but prescriptive analytics takes that prediction and recommends the optimal action, whether that's adjusting operating parameters, scheduling maintenance, or reallocating production loads. It combines machine learning, optimization algorithms, and real time data to simulate different decisions and identify the best possible outcome based on cost, risk, and efficiency. Instead of reacting to problems, systems can automatically guide decisions or even act autonomously. Prescriptive analytics is where IIoT shifts from monitoring operations to intelligently optimizing them.